Hi, girls. I hope you're doing well. Today we are starting something actually quite exciting. We are going to start working on trigonometry, or call it for short trig. So technically, you already read something about it, something very basic, and that is what we have here. So that if you are given a right angle triangle, which is the case here, so for this unit, we're essentially, at least for the beginning, only be working with right angle triangles. Otherwise, it just doesn't work. So you should know that by now there are names for the sides of a triangle, new names at least. You know the hypotenuse because we've worked with it for the Pythagorean theorem. Now we're going to be working with not only the sides of the triangle like we did for Pythagorean theorem, but we're also going to be working with the angles inside a triangle. So this angle here, the angle that we identify, it can be either angle. So if you've seen the video, you probably saw that in that case, depending what angle we use, the names will actually swap places. So for now, if we use this angle here that is on the left corner, then the side that is touching this angle will be called the adjacent, and the side that is not touching it would be called the opposite side. So without further ado, we're going to go, and I want to show you something that is super important, that is your foundation for trigonometry. So here, I just draw, for this first example, two triangles. I call it background but really it should be foundation. So first important thing, these are two right angle triangles. And then there's something really special about them is the fact that they have each an angle of 30 degrees. So what is important here that I want you to know this is that all the angles inside these two triangles are the same. And if you remember from last year, if you have triangles that have the same angles, then they are called similar triangles. So we are going to be working all with similar triangles, but at some point we're kind of going to forget about the fact that they're similar because they have to be, and it's not actually going to be super useful to use that fact anymore once we've figured out another really interesting fact. So they're similar, but they're not congruent. If you remember, congruent means identical because the side lengths are different. So now we're going to make a couple calculations because I want to show you something. So the first thing we have to do whenever we're working with trig is identify our sides. First side you should always identify is the hypotenuse because it's easy to see. It is the longest one. I'm going to try to write in a way that you can actually read. Hypotenuse. Okay. Then the next one would be the adjacent, the one touching the angle. So that's the one down here. And then finally the opposite, which is this one here. Okay. So what I want to show you here is one thing I could do is, for example, I'm going to start dividing the sides together. And I know that it's going to look weird for now, but just bear with me. So the first thing I'm going to do is I'm going to divide the opposite side with the hypotenuse. So in this case, the opposite is 2.5 and the hypotenuse is 5. So what do we get if we do that? I mean, we could do it using fraction, but let me just type that in my calculator. We get 0.5, 1/2. All right. Now let me just go right away to my other triangle. So this one, I'm going to do the same thing. I'm going to identify my side. So the hypotenuse is up here, the adjacent is here, and the opposite is here. So I'm going to do the same thing, and I'm going to divide the opposite side with the hypotenuse. So in this triangle here, the opposite side has 3.75 as length, and then 7.5 as length for the hypotenuse, meaning that if, again, I go ahead and divide this, 3.75 divided by 7.5, we get, again, 0.5. So do you notice here that no matter how big the triangle is, if I divide the opposite with the hypotenuse, I get 0.5. And if I want, I could keep on doing this for any similar triangle to this, and I would always get the same ratio between two sides. Let's go check to see if that works for any other side. The next one I want to try is the adjacent over the hypotenuse. So adjacent is 4.33. Hypotenuse is 5. For this, I get 0.86. So clearly it's different from this one. That's fine. Let's go and check for the other triangle here to see if I divide them, what number I get. So 6.5 is the adjacent, 7.5 is the hypotenuse. 6.5 divided by 7.5. And I get 0.86. Again, I'm going to highlight this in a different color. So here, if you notice, again, same number. Even though the side lengths are different, the ratio is the same. So let's go and do one last. I want to do, for the last one, I want to divide the opposite side over the adjacent side this time. So opposite is 2.5 and adjacent is 4.33. Let's go see what this is. 2.5 over 0.33, no, 4.33. I get 0.57 or 58, which again is different. But let's go see if I compare it with this triangle to see if this one works. Okay, so for this one we get 3.75 over 6.5. I get 0.58 again. So something special is going on here. We see that there's a trend, and that trend is that whenever you have similar triangles, similar right triangles, the ratios of the sides is always the same number. So if I told you I have a triangle with a 30-degree angle, and for example, for this one, I tell you that the hypotenuse is 2. Okay, so this is 90 degrees. So if the hypotenuse is 2, well, I can find the other two sides by doing the following. So we know, for example, that the ratio of the opposite over the hypotenuse is 0.5. So what I could do here is say, okay, well, we know that the hypotenuse is 2, and we are looking for the other side. So I could go ahead and find what the hypotenuse is pretty easily. The opposite side, right? Opposite is what I'm looking for. So I'm going to do 0.5, and then the hypotenuse is 2. So it means that my opposite, if I multiply by 2 on each side, is going to be equal to 1. So this side here is 1 because I know the ratio of the sides, right? Now, I could go ahead and find my adjacent because I know that the ratio of the adjacent over the hypotenuse, that's the second number here, is 0.86. We know that the hypotenuse is 2, 0.86, which means that my adjacent side in this triangle is going to be 0.86 times 2, which is 1.72. So as you can see, by just knowing what the angle inside the triangle is and one side, I can find all the other sides. So we would not be able to do this with the Pythagorean theorem because the Pythagorean theorem, you need two sides to find a remaining side, right? So in this case, what I'm telling you is that if you know the angle and one side, then you can finish this triangle and find all of the other information. So does it work? This works really well clearly for a 30-degree triangle. And I just told you that it would work for any two similar triangle, but it's not a necessity that the angle is 30. Let's go see what happens if we have a different angle. So I'm going to show you a second example here. So in this example here, our angle is different. We have an angle of 20 degrees. Let's go ahead and identify our sides. So again, longest side is the hypotenuse. I'm going to write this one first. The one that touches is the adjacent, and the one that is not touching is the opposite. Okay, same for the other triangle. Let's go ahead and do the other triangle while we're at it. So this one is significantly bigger. If you look, my first triangle has a hypotenuse of 3. This one has a hypotenuse of 35. So let's go see if it works when the triangles are so different. They're so different, but notice my angles are still the same. I still have an angle of 20 and an angle of 90, meaning that my two triangles are in fact similar. So this one here is opposite, and this one here is adjacent. So let's go ahead and calculate the ratios. First ratio I'm going to do is the same as I did above, which is opposite over hypotenuse. So opposite is 1, hypotenuse is 3. I'm not going to put this in decimals, or you can if you want, it's 0.33. Let's try this one. So if I have opposite over hypotenuse, so if I have 11.97 divided by 35 is about 0.3. Okay, so again, proven right that this angle and that this number and this number are the same. Let's do this again. I want to know, what do I want to know? I want to know the adjacent side over the hypotenuse. So adjacent in this case is going to be 2.82 over 3. It's 0.94. And then this one here, adjacent over hypotenuse, so 32.89 over 35. One thing I want you to notice maybe is how it seems like the two numbers here are pretty close together. 2.88 versus 3, and this one here, 32 or almost 33 versus 35. So you can see that they're kind of in the same, they're kind of close both cases, which is why the ratio should be the same. Let's see, 32.89 divided by 35. 0.94 again. Not much of a surprise anymore, huh? This one and this one. And then one last. We are going to do opposite over adjacent. So opposite over adjacent, we're going to have 1 over 2.82, which is 0.35. And then the opposite over the adjacent is going to be here, 11.97 over 32.89. That is indeed 0.35 again. All right, so now I'm trying different colors every time. You can see that for a 20-degree angle, it also works that even if my triangle is significantly bigger, the ratio of the sides is maintained. Now, if we compare these numbers with the numbers we had for the 30-degree angle, you can see they're different. So first ratio, we had 0.5. Now we have 0.33. Second ratio, 0.86 versus 0.94. And then third ratio, 0.58 over 0.35. And it makes sense that they're different because if you compare the first two triangles with the second two triangles, they're not similar. They're not similar at all. They have completely different angles. So if your angles is different, then the ratios are different. But if your triangles are similar, then the ratios are the same. So this is definitely something pretty powerful, but it's a little bit of a pain in the ass because if we have to start calculating ratios for one triangle and use them for the second triangle to be able to solve for it, we're never going to end. So let us give you some theory because these ratios that we just talked about are actually super important. I didn't pick the ratios of the sides by coincidence or because I felt like it. These three specific ratios that we did are so important that we gave them names. So let's talk about, this is a title that you should have. So we're going to have 3 trigonometric ratios for now. There's more. There's 6, I think. But we're only going to start with 3 of them. So the first ratio that we used in our example was the ratio opposite over hypotenuse. So I hope you can see it here. I can point, so it's pretty hard, but opposite over hypotenuse was equal to 0.5. That's the first one I did. And this one is going to be called sinus. So the first one here is called sinus, or sine, or sine. Okay, these are all different ways of writing it. The most common one I would say is probably the third one. But its full name would be sinus, coming from Latin or something. So so what this is here is, this is the ratio opposite over hypotenuse. So usually how we would write it is we would write sine of theta. Theta is the angle, remember? And that is the ratio opposite over hypotenuse. So we would write this all the time. So for example, in the first example, we had an angle of 30 degrees. And then we found out by calculating it that if we did opposite over adjacent, so here, then we got 0.5. So this number is going to be 0.5. So this literally means for any triangle, for any right angle triangle with an angle of 30, the ratio of the opposite over hypotenuse is 0.5. And we can do that for absolutely any angle. So that is our first ratio. Second ratio is called cosinus, or cosine, or cosine, or cos. Sorry, just like that. So these are the different ways to call the second ratio. Cosine is going to be the following. It's going to be the second ratio that we did, which was adjacent over hypotenuse. So for example, when we first did it, we did it with an angle of 30 degrees. So cosine of 30, we had found a number for that. I don't remember what it is. Let's go check. So the number, so it's the second one, the one in pink, it's 0.86. So cosine of 30 is 0.86. And what this means is that the ratio of the adjacent and hypotenuse for an angle of 30 degrees is always 0.86. There was one last ratio that we worked with, and that was the tangent ratio. Tangent, just like that. We also call it tan. We only have 2 of them for that. In Bulgaria, they write TG. So I guess these are all the ways you can write that down. So in this case here, the tangent was our last ratio. If you remember, that was the opposite side over the hypotenuse. No, over the adjacent. Sorry. Over the adjacent. So what we had found, for example, is that tan of 30. So if I have a right angle triangle with an angle of 30, then the ratio of the opposite over the adjacent is the one in green, and that is 0.58. Okay, so these were just for my examples. So write this down. This is super important. You will have to remember all of the ratios by heart. Like, this is something you need to know. And then I'm going to give you another video that kind of gives you another explanation for this and tricks to remember what the ratios are. Okay, so the other thing I want to show you is that it's all good. Like, it's nice to know that there's ratios like that, but how do you know what the ratio is for any angle? So for example, if I ask you to solve for a triangle that has an angle of, I don't know, 36 degrees, like, that's pretty random, right? So back in the days, thankfully we have a better way of doing this now. They had this wonderful table here. Look at that. So you have in the yellow section here, all of the angles. That's not what I wanted to do. So you've got all your angles, then you've got your sine, your cosine, and your tangent. So if we go to the 30-degree one, we should have, we already did it, right? So we found out by doing it that 30 degrees right here, that the first ratio was 0.5, second ratio was 0.86, and last ratio was 0.57. So these numbers, we had found them ourselves right here in the first example, 0.5, 0.86, 0.58. But then again, like I told you, if you want to do it for a 36-degree angle, then these numbers don't work. So what you could do is go ahead and in this table and then found all the numbers that work for a 36-degree angle. We could also look for the 20-degree angle that we did for second example. So 0.34, 0.94, and 0.36 were the numbers we had gotten. The table tells us, and that's pretty much what we found here. Okay, so we found 0.35. Maybe I was not super precise, but the other numbers match. So this table here can be super useful because, as you can see, whatever the angle is, you can go in it and find what the ratio is that you need. Like I said, this method is not used anymore because it becomes a problem if, for example, I'm asking you for an angle of 30, no, let me stop with 30, 85.3. Then this table does not have 85.3. It has 85, it has 86, but it does not have 85.3. So we have calculators nowadays, and the calculator can do it for absolutely any number. So I'm going to ask you guys to take out your scientific calculator and look here. We have sine right here, cosine right here, and tan right here. So what I want you to do right now is check to make sure it works. So write sine, and then type sine on your calculator, press on that button, and then write 30, and then make equal. You should get 0.5 once you press equal. Try the same for cosine of 30. What did we get for cosine of 30? I don't remember. Let's check. We had 0.86. So type cosine 30 and then equal. You should get 0.86. You can do the same thing for tangent. So type tangent of 30. And then once you do that, you should get 0.57. You're going to get a lot more decimals because your calculator is super precise, as opposed to us, which were a little lazy on only keeping 2 decimal points. So try that and let me know if it worked. Let me know if you have any questions. I'm going to give you more stuff to do on that today. See you guys.